Okay, are there any questions about Chapter 11 stuff? I know they're due tonight. People emailed me, are they really due tomorrow? Yes. But I have to schedule that before the exam because I'd like you to get done with them before the exam so you have time to practice. So if you don't quite get them done tonight, by Wednesday would be appropriate. So you still have some time to look at the exam. So the exam on Friday is going to look very similar to the third exams from previous years, at least the later ones. So this will be the first one that totally, I think all the material that is on those older exams will potentially be on this one. So you can use those as practice exams or additional practice problems if necessary. No questions? Okay, so then we'll continue on with alkene reactions. And we'll talk a little bit about how we can determine if something is stereo or regio selective. A little bit more of the rules. So let's just kind of, to get our heads kind of back into this, what reactions do we have? We have, we started with, okay. We started with HX. Addition. Then we have BR2 addition. We have BR2 and H2O. Then we have H plus H2O. And I don't know why this is like completely writing everything when the pen moves. So, other than it's Monday and it's the first day after break. So, with H plus H2O, we also then have H plus ROH. And then we taught, then I think that was that it? I think that was everything. Oh, we could have BR2 and an alcohol, which would follow the same rules as BR2 and water. So I think that's all the reactions that we had to date. And now we'll add a few more on here. And the few more that we'll add, we'll start with adding H2 to an alkene. So if I take my alkene, this is just... So if we want to add an alkene, we're going to add H2 and palladium. So So we're going to be adding 2 H's across the double bond. Okay. And this reaction is what we call hydrogenation. Is what it's called. So in the hydrogenation reaction, we're going to add 2 H's across the double bond. So my first question would be, just to get our minds back into this, can this reaction be or can it be regioselective? And I'll go ahead and just, is it regioselective? We'll make this multiple choice. So regioselective, A, yes. The B, no. Guys, everybody have an answer? I didn't count. And those of you who logged in from home last week, I saw you logging in from home last week, so hopefully you were able to see what the questions were. All right, let's see what we got. Okay, we've got 10 A's and 19 B's. So regioselective? No. It's not regioselective. Why not? Melanie? So the adding to one side or the other is stereoselective. No. Remember, regioselectivity is if I add the hydrogens this way and this way, I get 2 different products. Hydrogenation cannot be regioselective because of why? What about the hydrogen? It's a blank reagent. Starts with S. Boy, just imagine how organic 2 after Christmas break's going to be. That's okay. I have something up my sleeve there. Symmetrical. So whenever you add a symmetrical reagent, it cannot be regioselective, because adding two hydrogens one way and then adding them the other way gives me the same product. So when you look at the reagents that I have over here, the ones that cannot be regioselective, and I'll just put an R with a through it. This one cannot be regioselective. Because of the reagent. So if I put H2 down here, it cannot be regioselective. Now, it cannot be regioselective because it itself is a reagent. These other ones could be not regioselective because the alkene that we're using is symmetrical. So remember that whenever you have a symmetrical alkene or reagent, the reaction is not regioselective. It's not regioselective. So with a lot of these rules, and I'm going to kind of go back and we're going to have to remember these from what we talked about last week and the week before, it's sometimes easier to think of when it isn't than when it is. Okay. So it's not regioselective because it's a symmetrical reagent. So both bromination and hydrogenation will never be regioselective. But the rest of them could be. Okay. Right. Now, hydrogenation is has a mechanism that I don't know that it's completely understood, but what I'm going to show you is kind of what makes the most sense. But more importantly, whenever you add, so in other words, if I have dimethylcyclohexane and I add H2 and palladium or platinum, okay? So in this reaction, what happens is the palladium or the platinum metal catalyst, well, it is a catalyst. And so what happens is that if you can imagine, if you have a platinum or a palladium metal surface, the hydrogen comes down and it basically adsorbs onto the surface of the palladium or platinum catalyst. And when it does, it kind of breaks apart into hydrogen atoms. That part is, I don't think, fully understood. And this is a fairly important reaction. I mean, it's used every day in certain industries like refineries. But I'll talk about that in a minute. So the hydrogen adsorbs onto the surface of the platinum or the palladium metal catalyst. Then the alkene comes down and approaches that catalyst with its pi bond. And so what happens is that both hydrogens add at the same time. And we could draw the arrows where they kind of look like this, because I'm going to draw these other arrows later on. So we could kind of say, okay, the double bond takes its pair of electrons to bond that hydrogen, and then the hydrogen-hydrogen bond breaks, and that pair of electrons moves to bond the hydrogen to the other carbon. So we kind of have a transition state that looks like this. So that's a square transition state. And a square transition state always leads to 100% cis addition. So we have 100% cis addition of the hydrogens to the double bond. And that's the hydrogenation process. Is we do end up with 100% cis addition. So I'm not going to ask you to do that mechanism. I could ask you to do some of the other mechanisms, and you'll see on the older exams that I have done that. But when we have a square transition state, there's just no room for the hydrogens, if they both have to add at the same time, they have to add to the same side of the double bond. The ring isn't big enough for one hydrogen to add to one side and for it to add to the other. So this is 100% cis addition. So if I took this reaction right here and I said, okay, what's the major product of this reaction? I could write the product by simply knowing question number 1 and number 2 and number 3. So question number 1 is, what's being added to the double bond? 2 H's. Okay, then I've got my CH3s. So I'm adding 2 H's. How am I adding them? Markovnikov or anti-Markovnikov? Doesn't matter because there is no Markovnikov or anti-Markovnikov because it's a symmetrical reagent. Then question 3, 100% cis, trans, or both, 100% cis. So all I have to do is make sure that the 2 hydrogens have the same wedge, and then the methyl groups, or whatever groups are on the ring before that, will automatically get the other one. And it doesn't matter whether the hydrogens were on the bold wedge or the dashed wedge, but they have to be on both the same wedges to indicate that they added cis. So that would be the major and only product of the reaction. For this reaction. Now, let me ask a question. Is this reaction regioselective? That should be a quick answer. No. Why not? Because hydrogen is symmetrical, right? If that's new, where have you been for the last 10 minutes? So it's not regioselective, but is it stereoselective in this case? In order to answer that question, what I need to do is I need to add the hydrogens trans. Now I know 0% trans, right? It's 100% cis and 0% trans. But is the trans a possible product? Yes. Whenever we're talking about looking at regio and stereoselectivity, we can take any alkene we want and any reagent and we say, let's add the groups this way, and then let's add them this way, and see, did they produce 2 different products? In this case, no, so it's not regioselective. Then we add the two groups of our reagent, 100% cis and 100% trans, and we say, are those 2 products the same or are they different? And in this case, what are these 2 products? Are they the same or different? Different? Do we agree that they're different? Then why didn't you say it? Okay, different. Well, specifically, what's the relationship between those 2 products? Are they enantiomers? Are they diastereomers? Whenever we're talking about adding something 100% cis and 100% trans, we're now in the stereochemistry realm. There are 2 different stereoisomers. Are they 2 different stereoisomers? What kind could they be? Enantiomers, diastereomers. So these 2 are what? Hannah? Do we agree that they're diastereomers? Yes? No? How are they diastereomers? Top carbon has what? Same configuration. Bottom carbon has opposite configuration. That makes them diastereomers. So these two are diastereomers. Did the reaction select one over the other? Yes. Again, it doesn't matter whether it's selected at 50.5 to 49.5 all the way up to 100.0. It's selective if it chose one over the other, even if it chose one exclusively. The other product is possible. And if the other product is a different stereoisomer, then we chose one stereoisomer over another. That makes the reaction stereoselective. So this reaction is stereoselective. But it's not regioselective. Now, for stereoselectivity to occur, you need to make products with at least two chiral centers. Okay. If you make a molecule with just a single chiral center, remember that our rules are you could only make one enantiomer over another if you had a chiral reagent. So we're not going to have a chiral reagent in any of these reactions. Okay. So you need to have more than one chiral center in the product. And again, you're only going to have stereoselectivity when you have a triangular intermediate, because then you're adding 100% trans, or now a square intermediate when you add 100% cis. But it doesn't guarantee that the reaction is stereoselective. It just means it could be stereoselective. Does that make sense? Probably will after you do some problems and stuff. So I think in the folder there's every combination of cyclohexane, because if I change the cyclohexane molecule, I can change whether it's regio or stereoselective for any of those reagents that we've done so far, for instance. And this is how I would ask you. If I gave you this problem and I said, number one, write the major product, I might say, well, I probably would just say write the major product of the reaction. So you would write the major product of the reaction. And in doing so, you would need to know, what am I adding? What groups am I adding? Am I adding a Markovnikov or anti-Markovnikov? Am I adding them 100% cis, 100% trans, or both? So you would write that product. Everybody written that product? You could have the hydrogens on two dashed wedges, but If you have something like that where the hydrogens are on the same wedge, then you have the correct product. So then my next question is it regioselective, stereoselective, both, or neither? Regio, stereo, both, or neither? Okay, let's see what we've got. We've got 20 Bs. What's B? Stereo. Okay. Should have seen if anybody said regio. Some people said both. Can't be regio, right? So it can't be both. So that takes out A and C. Stereo or neither? Well, I might have suckered you into this answer, but remember there's a hydrogen there too. So now when we look at this molecule, my first question is, if I add the hydrogens 100% cis and 100% trans, do I get two different products? And if I do get two different products, they're going to have two chiral centers. So my question about this product is, how many chiral centers does it have? Ashton? How many people agree that it has one chiral center? Okay, give me another number. 0. How many people think that it has 0 chiral centers? You're all by yourself. It's okay. It has 0 chiral centers. Remember, mirror plane cuts through. Whenever you have a monosubstituted, I shouldn't say remember, because that was a long time ago that we talked about stereochemistry. But when you have a monosubstituted ring, there's no chiral centers because the mirror plane cuts through the molecule. By putting these hydrogens in bold and dashed wedges, I'm kind of being deceptive, aren't I? Because to be honest with you, we would normally represent them that way, without them even being there. So when you pass the mirror plane, it goes right through the center of the hydrogen, right through the center of the methyl group. because remember, those are axial and equatorial. So there are 0 chiral centers in this molecule. And when you have 0 chiral centers or 1 chiral center, the reaction cannot be stereoselective. And remember, it has to select. It has to select something. So the only way it could potentially select something is if it's 100% cis or 100% trans. If it's not 100% cis and it's not 100% trans, then it's going to be 50-50, and whenever it's 50-50, it can't be it can't be stereoselective. Right, so we have to take each one of these reactions individually. I lose one methyl group, no selectivity. I put another one in, it's stereoselective. I take this one away, it's still not stereoselective. It's still not regioselective. Okay. So there are a bunch of problems in the folder that have this permutation of molecules. I don't know how hard I'm going to hit this on Friday's exam because it's one of these things that we need to do a lot of problems. And the lot of problems that you need to do right now are chapter 11, right? And not the twice around the alphabet number of problems that I have in my set. But we do have to think about the basics. So if you have to make 2 chiral centers for it to be possibly stereoselective. All right, that's just one reaction. That's hydrogenation. What else do we have? Another reaction that we can do, let me talk about hydrogenation's importance. So hydrogenation is important to turn alkenes into alkanes. And since it adds 100% cis, probably the thing that it's used the most for is to convert these kinds of molecules into to convert these molecules from one form to another. So does anybody know what this is from biology? This alcohol right here, when it's released, if it's CH2OH, CHOH, CH2OH, that 3-carbon alcohol is glycerol. When you attach a long-chained carboxylic acid to each of those and make a triglyceride. And what's a triglyceride normally known as? This is a fatty acid. So it's made from glycerol and a fatty acid. And fatty acids have long chains. So a triglyceride can either be a solid fat or a liquid oil. And that's literally the difference between a fat and an oil. Fat's solid, oil's liquid. So, there's good fats and bad fats, and better yet, there's what we call saturated fat, in which all the carbons are single bonds because they are maxed out at the number of hydrogens, hence the term saturated. Alkanes are saturated. Or you can have an unsaturated fat. Where there's some multiple bonds in the double bond. So we have saturated fats and we have unsaturated fats. So depending upon the composition, a saturated fat tends to be a solid, and an unsaturated fat tends to be an oil. And it's because the double bond kind of kinks the chain so that they don't pack very well. And so if they don't pack very well, they tend to have a higher melting point. So you have solid fats and liquid oils. So your vegetable oil, unsaturated, your solid fat, I don't know, like coconut, butters, are saturated. I forget which one is healthy and which one isn't. I think it's like everything else, moderation. But what they do is they take the liquid oil and they convert it to the solid fat by using hydrogen and palladium. So that's how it's converted. That's how you can convert the oil into the fat. And of course, when you do that, you make sort of an artificial fat, like Crisco, or back in the old days, what they called oleo. If you have the really old cookbooks, they'll say use oleo, and what's oleo? I think it's just Crisco. But then what happens is you don't completely convert all the double bonds, and so you end up with your partially hydrogenated fats. And I do think I remember that those will kill you. Or at least that's what people over a long time, they're not healthy. So when you go to the supermarket and you buy Crisco, it's a hydrogenated oil. So that's where we see that terminology in real life. And then you can have cis fats and trans fats. I forget which one of those are good and bad, but that's how they interconvert one into the other. In the refining process, if they just want alkanes, crude oil has both alkenes, alkanes, and alkynes. Mostly alkanes, few alkenes, even fewer alkynes. And if you want to convert the alkenes into alkanes, at the refinery, you've got to hydrogenate them as well. And then you have to make sure your catalyst doesn't get poisoned in the process, because when it gets poisoned, it doesn't react very well. And we'll talk about poisoned catalysts next semester with alkynes. So that's their real life purpose. All right, another reaction. Let's look at this one. I've actually got, I think, 2 more additions. So this is called hydroboration oxidation. It's a 2-step reaction. And I should have said that hydrogenation is a reduction reaction. Okay, so if we go back here, hydrogenation is a reduction reaction. And in organic chemistry, we talk about reduction in terms of it's an addition of hydrogen to the molecule, or it's a loss of oxygen. That's reduction. Oxidation, in organic chemistry, we typically talk about adding oxygen or losing hydrogen. Those are the way we define oxidation reduction in organic. And the reason for that is because we don't normally look at the oxidation number of carbon. Okay? Because that's a little bit trickier than it was in general chemistry. It's not that hard. But we don't normally track the oxidation state of the carbon. And if we do, it usually correlates with adding or losing oxygen or hydrogen. So this is a little bit different way of looking at oxidation reduction than in general chemistry, where you have the oil rig, which I don't know what those mean. I use Leo, the lion goes grr, for lose electrons oxidation, gain electrons reduction. I guess we lose the I's. Oxidation, lose, electrons reduction, gain. To me, that's a stretch. The E at least tells you something. So anyway, that's how we define this. So hydrogenation is a reduction reaction. Very much like what we did in lab. Right? When we did the yeast reduction, if you remember, and why wouldn't you? It's only been a few weeks. And the lab reports due this week, I think. But remember, we took the ketone part and we added 2 hydrogens to it to make our our ethyl hydroxy butanoate. Now, had we have used hydrogen and palladium to add across the double bond, which just accept that would have worked. If we would have done that type of reduction, we would have ended up with a racemic mixture. So the fact is, our net result with the enzymes in the yeast was the same thing, but now we gained a chiral molecule. So that's what we did there. So when I say oxidation, I'm going to add oxygens to the second part of the reaction. And the oxidizing reagent is hydrogen peroxide. Okay? That's what hydrogen peroxide does, is it oxidizes things, which means it adds oxygen to molecules. Okay. So the first question is, what's the first step in the reaction? And the first step in the reaction is this. I'm going to take my double bond and I'm going to add to it a BH3. But I'm going to add the H and the rest of the boron group. Now, boron is less electronegative than hydrogen, so that makes the hydrogen a minus and the boron a plus. So this is called borane, and it basically has the hydrogen having a negative charge. Okay, that's whenever you have a hydrogen having a negative charge, that's called a hydride molecule. And a hydride is different than a proton in terms of its reactivity. Protons are electrophiles, hydrides are nucleophiles. So we can change the character of hydrogen by attaching it to an electropositive element like boron. So what happens is this. I'm going to draw the arrows the same way I did with the hydrogen gas being absorbed onto the surface of the platinum or palladium. Meaning I'm going to take this pair of electrons, give it to the hydrogen to form the CH bond, and then take this pair of electrons from the double bond and give it to the boron to form a C-Br bond. So I'm going to go through a square transition state. Just like I saw before. So then I could say to you, well, how are the boron and the hydrogen going to add? Because it's now a square. They're going to add 100% cis. And then I'll have the hydrogen added to one carbon and the BH2 added to the other. So I've added a hydrogen. Then, once I form that molecule, and I'll come back in a minute and expand on this. But once I add the boron to the carbon, I then treat this with hydrogen peroxide, and what happens is the BH2 now becomes an OH by a mechanism that we're not going to talk about. But what's critical is that the hydrogen and the boron added cis, the OH is going to replace the boron in exactly the same position. So the OH and the H are going to add 100% cis to the double bond. So the hydroboration is the addition of the borane, and then the second reaction is the oxidation with hydrogen peroxide. So ultimately, with hydroboration oxidation, what am I adding? I'm adding an H and an OH, 100% cis. Now, I'm leaving out question 2, which is Markovnikov or anti-Markovnikov. Well, okay, Markovnikov and anti-Markovnikov in the sense that, well, in Markovnikov's rule sense. I'm adding an H. Which H do I add to? In this case, the boron adds to the least hindered carbon. It adds to the least hindered carbon. And the question is why? Well, if you'd accept that BH3 is a bigger group than the hydrogen, then adding the bigger group to the less sterically hindered hydrogen is going to have a lower transition state because there's less stuff running into each other, less steric hindrance. But actually what happens is that once the boron adds to the first carbon, it then adds to another double bond, so that at the end, after all 3 of the hydrogens have been added to 3 alkenes, the real structure looks like this. It has 3 borons with the 3 groups added to it. So you only need 1/3 of a mole equivalent of boron because it will add all 3 of its hydrides to double bonds. And so this molecule is really sensitive so that the boron has to be on the least sterically hindered carbon. Because I don't just have one of these molecules, I've got 3 of them. So this then adds anti-Markovnikov. And this is the first anti-Markovnikov reaction that we have. So in other words, the hydrogen adds to the carbon with the least hydrogens, and the boron adds to the carbon with the most hydrogens, because that's the least sterically hindered carbon. So that leads to 100% cis and an anti-Markovnikov addition of OH. So we'll leave it at that. But I will just say there's a yin and a yang of chemistry where you'd like to be able to add groups this way and then have another set of reagents that would add them this way. For alcohols, H plus H2O adds Markovnikov. Hydroboration oxidation adds the OH anti-Markovnikov. So now we have an ability to make both kinds of alcohols when we want to, which is part of what the reason organic chemistry is important, because if I have these reactions do it this way and then do it opposite, that makes things more useful. So we'll leave off. This will be the end of the reactions for the exam. And I've kind of taken them a little bit out of order, so you might see some reagents on the older tests that aren't part of this. But going back to the beginning then, we added H2, and then we did BH3, H2O2. So I think that is a comprehensive list of, but nothing's comprehensive because I can't guarantee that I'm remembering everything. But you have notes, you can go through them. Okay. All right, so if you have any questions, on Wednesday we'll use it as a question day. If we stare at each other awkwardly for more than 2 minutes, then I will continue on with alkenes. So